how could scientists know how old something really is? We hear about a mammoth from 10,000 years ago, a triceratops from 70 million years ago, petrified trees from 200 million years ago, that the Earth is around 4.5 billion years old, and that our universe is 13.7 billion years old. What are the nuts and bolts of scientific dating that allow for such seemingly accurate estimates? I'm your mental curator, Johnny Hemberger. I am a severely curious person, and you are listening to the Beyond Bones podcast, presented by the world-renowned Houston Museum of Natural Science. Stop by and visit us soon. You can also drop us a line at podcasts@hmns.org if you'd like to suggest future topics or just leave us a comment. All this information and more can be found in the episode description. But without further ado, make sure your clocks are set correctly, and let's explore the brass tacks of scientific dating. Scientific dating sounds like two people in lab coats meeting at the Cheesecake Factory to learn about each other over 4,000-calorie desserts. And perhaps that's not wrong, but let's be specific. When you read that the Earth is 4.5 billion years old, or that dinosaurs died off around 67 million years ago, or even that we found a 6,000-year-old mammoth, how do scientists know that? And perhaps rhetorically, how can you trust this information? I'll be real with y'all here. I also manage our YouTube account. I read the comments daily, and when I upload anything having to do with paleontology, astronomy, or any other facet of science that deals in thousands, millions, or even billions of years, to say those comment sections are filled with doubters is an understatement. But whether or not they are trolling, or even if they are entrenched in their worldview, the question in dispute is a good one. How can scientists speak to the age of our universe and the contents within with such confidence? First, I'll start where I think most of us lay people do, with just enough knowledge to think we know everything and not a single milligram more to realize we don't. A lot of us heard the elevator pitch of carbon dating in middle school science class. We filled in the correct answer on the Scantron, then moved on with our lives, ready to crush it when we are asked about scientific dating on Who Wants to Be a Millionaire. Now, some of us picked up along the way that carbon dating is quote-unquote flawed because it's only accurate to several thousand years at best. Going further down the rabbit hole reveals that carbon dating can actually be wildly inaccurate due to chemical contamination and other factors and variables. So for some of us, that was that. Carbon dating is unreliable, so science is wrong. We've closed that book in our minds and perhaps entrenched in our own flavor of conspiracy.
Scientists are simply under the full control of the Illuminati, the humanoid reptilians living underground, and the tall gray aliens that are really pulling the strings and building our pyramids.
Fine, to each their own. But just like darn near everything else in life, there is much more to real understanding. I'll start with this, perhaps, bombshell. There are many, many more methods to estimate timescale than just carbon dating. Heck, there are dozens more options using radiometric dating alone. Uranium-lead dating, samarium-neodymium dating, and potassium-argon dating, just to rattle off a few, and that's just the tip of the iceberg. As you can tell, we can get very, very into the weeds with the inner complexity of radiometric dating. But let's start with a general synopsis of how it works. With a tree, you can just cut it down and count the rings to come up with an age estimate. Bada bing, bada boom. Radiometric dating is a little different though, so let's start with the ever so hyped carbon dating. The half-life of the carbon-14 isotope is 5,730 years. Half-life means the amount of time for half of the atomic nuclei to decay. A grossly oversimplified way to think about half-life is to imagine water evaporating from a cup. If you know how quickly the water evaporates until the cup is half empty, then you can estimate when it was filled. assuming the weather each day is unchanging for this exercise. So for mental example, if you notice that it takes 10 days for a full cup of water to evaporate down to half empty, the half-life is 10 days. Then, just by randomly glancing at the cup on any random day, you can tell when it was filled. But, kinda like water, carbon-14 quote-unquote evaporates relatively quickly. So if you find a cup with only residue left over, it becomes more difficult to estimate the further from empty it gets. Was this filled 20 days ago or 20 years ago? Eventually there's not enough carbon-14, or in this case water, left to accurately measure. Now, like I mentioned a few moments ago, there is a mind-boggling gulf of information between different dating methods, how and when to apply them, and how and when to test them. There's also a margin of error for each. Suffice to say, there are more accurate methods to use when carbon-14 cannot be. Speaking of margin of error, earlier I mentioned that scientists believe the universe to be around 13.7 billion years old. The margin of error in that estimation is about 200 million years, so the universe is really between 13.5 billion years old and 13.9 billion years old. 200 million years sounds almost laughably inaccurate. But is it? Should we throw the baby out with the bathwater? Absolutely not. At this scale, 200 million years is a margin of error around, are you ready for this? 0.01%. 200 million years is about 0.01% of 13.7 billion. In other words, we know with 99.99% accuracy that the universe is 13.7 billion years old.
Okay, mental curator, how do you know that? How do scientists measure the age of the universe if not only does carbon-14 dating not apply, but is only accurate to a few thousand years, let alone billions?
Good question, metaphorical listener. There are a number of methods scientists use to determine the age of the universe. One of the most accurate ways is to observe the rate of expansion. It is relatively constant no matter which direction you point the telescope. The rate of expansion is called the Hubble constant. It is measured, stay with me now, in kilometers per second per megaparsec. Specifically, 73 kilometers per second per megaparsec. Toss that out nonchalantly to impress at your next dinner party. Nobody will think you're weird at all. Oh, and sorry, Han Solo, a parsec is a measure of distance, not time. Without getting too far into the weeds, a parsec is roughly a distance of 3.26 light years measured on a curve, accounting for parallax, and you know what? We'll just leave parsecs there for the purposes of this episode. Anyway, measuring the expansion of the universe is kinda like those math problems in school. If a car passes you and it is traveling at 100 miles per hour, how far away would it be in 1 hour? Assuming it's going straight. But not only is the car moving, it is also blaring its horn. As it approaches you, its pitch goes higher and higher, and then when it passes you, the pitch gets lower and lower. The Doppler effect, as it's known. In astronomy, this is called the red or blue shift of the light spectrum. If an object appears blue, it is moving towards you, like the horn pitch rising as it approaches. If an object appears red, then it is moving away from you, like the horn pitch getting lower after it passes. Think of holding a rubber band. Stretching away from you pulls the wavelengths apart into the red spectrum. Pulling it back towards you shortens the wavelength into the blue spectrum. Roy G. Biv, baby. But back to the universe. Since the rate of expansion is constant, all you do is note an object's position a few times and you'll have a fairly accurate estimate of where it started and where it is going, and most importantly, when it started moving. That galaxy is going to take 1 billion years to get there, so from the quote-unquote center of the universe, it took 10 billion years to get here. In other words, that car from the school math quiz is 1,000 miles away going 100 miles per hour, which means it was here 10 hours ago. The oldest parts of the universe we can observe are 46.5 billion light years away, and since expansion is relatively constant, we can estimate when it started expanding. Our HMNS astronomer James Wooten explains further.
And by noticing how big the redshift is, we know how fast the galaxies are receding. We can tell that the galaxies farther away are receding even farther, even faster than the ones nearby. And therefore we can just rewind the clock in our minds, and that brings everything back to a certain point, and it takes a certain time to do that. And that's the estimated age of the universe. It's based on the observed expansion of the universe, called the Hubble constant. There's something you can measure in how galaxies are receding based on their redshift.
All well and dandy. That's the age of the universe sorted. Let's come back down to Earth and figure out how old this Triceratops shin bone is. A good place to start would be the infamous asteroid strike that killed it and its enemies in a blaze of glory. Well, before slowly starving and freezing a lot more species to death after the initial strike. Scientists believe that this extinction event asteroid strike occurred around 67 million years ago.
Wait, Johnny, when I grew up, it was 65 million years ago. Y'all keep moving the goalposts.
Good observation. The goalposts weren't moved, they've just been placed more accurately as more accurate methods have been tested and applied. It's like bringing a camera lens into sharper focus. So, the asteroid strike, technically known as the Chicxulub asteroid that impacted near modern-day Chicxulub, Mexico. When large asteroids impact the Earth, they create some very unique minerals, chemicals, and geological phenomena in that forge of unfathomable violence.
Forge of Unfathomable Violence.
What a cool name for a band. Anyways, in other words, it leaves unmistakable evidence beyond just a massive crater. Some of this evidence, especially for an impact of this size, uniformly covers the entire planet. It can be found in the exact same location of the geological record, whether you are in Houston, Rome, and even beneath your feet on your blind date to the Cheesecake Factory. An unmistakable layer of the Earth cake. Specifically, a layer infused with iridium. Iridium is extremely rare on Earth. However, it is abundant in asteroids and thus meteorites. Our Houston Museum of Natural Science paleontology lab technician Ryan Price explains further.
When the asteroid, the meteor, came down, plowed into the Earth and exploded, right? All that iridium got vaporized. That iridium had to come back down, right? And as it settled on the Earth, it created a literal layer that was infused with that iridium. And that layer has been found all over the globe. You can find it in North America, right? You can find it in Europe. You can find it in Africa. It's really famous, right? You can point at it. And they have been able to date that particular layer because of what it is. And they can get an age estimate for that. And the really neat thing, the way that we could prove it's around that point, right, is that no matter where you go in the world, no matter where you find that layer, no matter where you sample, you will never find a non-avian dinosaur above it. And it will always sit at around 66 million years ago.
Think of asteroids like leftover bricks from the construction of the solar system. Our solar system started as a cloud of gas and molecular dust. A nearby star went supernova, and the shockwave from that event forged these molecules into heavier elements. That's the theory anyways. Also, much of that hydrogen cloud condensed under its own gravity to ignite our sun. Heavy metals are formed by supernova due to the insane forces forging elements together under the immense heat and pressure of that explosion. One of these heavy metals is lead. Remember I mentioned that there are many more methods of radiometric dating than just measuring carbon-14? Well, one of those is lead-lead dating. Specifically, the ratio of lead isotope 207 to lead isotope 206. Depending on that ratio, you can determine how old the sample is. The math is beyond complicated, but it is sound and most importantly, repeatable. Trouble is, most rock on Earth has been melted and remelted over and over again by plate tectonics. earthquakes and all that. For instance, making its way to the surface through volcanic activity, only to sink back down into Earth's mantle as the plates of the crust shift and sink under each other over time. But you know what rocks haven't changed since the formation of the solar system? Yeah, asteroids. When they fall to the Earth as meteorites and we find the pieces, guess what the lead-lead isotope ratio reveals? Yep, about 4.5 billion years. Moon rocks we've brought back to Earth? 4.5 billion. Find a new meteorite? 4.5 billion. Old meteorite? 4.5 billion. Several radiometric dating methods confirm this, not just lead-lead. That's critical in science. Multiple methods of testing, each with the same results. So, the solar system, and thus the Earth, is around 4.5 billion years old, with a margin of error around 50 million years, or about 1%. There are dozens more highly refined methods of radiometric dating and otherwise used to determine the age of the geology within the Earth's layers, not the least of which is the simple context in which a specimen is found. We have a very solid, repeatedly tested and validated estimate that the extinction asteroid hit about 67 million years ago. Our Triceratops fossil was found a certain distance beneath that layer of ash. Thus, this fossil is around 70 million years old. This petrified tree trunk is even deeper in the geological layers from the 67 million year ago asteroid impact, deep into the neighborhood of 200 million years. Oh wow, here's a nicely articulated ichthyosaur fossil skeleton 10 feet away in that same layer. It is reasonable, then, that this ichthyosaur died around 200 million years ago as well. Oh, here's a turtle a few feet above the ichthyosaur. That's, naturally, a few million years closer to modern day. Oh wow, this 90 million year old crocodile fossil looks extremely similar to modern crocs. I wonder why this species survived the asteroid extinction event. At any rate, let's start wrapping up this episode by turning the geological clock closer to modern day. It is super convenient that human beings started jotting things down as early as 37,000 years ago, but really hitting their grammatical stride around 4,000 years ago. This event occurred 2,000 years ago because several sources literally wrote it down at the same time. Remember carbon dating? It's super accurate at this scale as well. Quote-unquote cavemen are drawing pictures of woolly mammoths, and we've carbon dated their chalky, not yet fully mineralized bones, lo and behold, to the same time that humans were documenting them. Scientific dating and context clues confirming each other's timelines. It's beautiful. But before we go, I'm going to play devil's advocate in a very specific argument.
Mental curator, wooden ladders and hot spring pools fossilize within a few years, even months. So, dinosaur fossils probably fossilized within the last few thousand years at most.
So, here's the thing about that. Those ladders quickly develop a layer of mineral deposits. They are solid as a rock, but at the center is still the wooden beams of the ladder. The wood has not mineralized. It only gained an exterior crust of mineral deposits. Dinosaur fossils have mineralized, meaning there is no bone left. Minerals, mainly calcium, have replaced the bone itself over time. A long time. Fossilized wood, like the 200 million year old tree trunk mentioned earlier, are no longer wood. The cells of the tree have literally been replaced by minerals. In other words, it has become solid rock through and through. Here's what I hope the takeaway is from this episode. We fear what we do not understand. So if this episode gets you even one timid footstep closer to understanding, then we have less to fear. My hope with this episode of Beyond Bones, and every episode for that matter, is to leave you with at least a smidgen more understanding of the world around us. That some of you may then be inspired to do further research on your own, because if we even slightly better understand our world, then we can be slightly less fearful and thus slightly more kind to one another. It is estimated that the sun has about 5 billion years of juice left. It is too small to explode in a supernova, but will become a red giant star, theoretically engulfing our planet. Sounds scary. But the way I see it, we've got billions of years to pursue understanding, and our own blink of a lifetime to contribute our small part towards compassion. Thank you for listening to the Beyond Bones podcast from the Houston Museum of Natural Science. I've been your mental curator, Johnny Hamburger. Come by and visit us, but as always, stay safe and stay curious.